Geotechnical engineering is the story of the engineering relationship between humans and Earth. It is the science that explains the mechanics of soils and rocks and its engineering applications to the development of humankind. In early times, the practice of geotechnical engineering was applied by trial and error, observational experience, and empirical experimentation. Problems such as the notorious Leaning Tower of Pisa prompted engineers to begin taking a more scientifically based approach to geotechnical engineering. From the early 1700s to the early 1900s, scientists such as Coulomb, Darcy, Rainkin, Basinesque, Moore, and Atterberg published fundamental theories on soil mechanics and water flow through soil. Several prominent organizations and societies were formed in the early 1900s to advance this field of civil engineering. Particular recognition is given to Karl Terzaghi, who is considered to be the father of modern geotechnics with his classic book on soil mechanics published in 1925.
In 1936, along with fellow colleagues from 20 different countries, Terzaghi founded the International Society for Soil Mechanics and Geotechnical Engineering. He became its first president. Today, the International Society has more than 89 country members involving over 19,000 individuals in the geotechnical engineering profession.
Most of what geotechnical engineers do is hidden below the ground surface, yet it is a very important discipline with a vast scope, as all construction has to rest on or in the ground. Soil is a complex material, which is very variable in grain size, cementation, strength, and behavior. This renders the task of the geotechnical engineer among the most challenging tasks in civil engineering. Geotechnical engineers use fundamental principles of soil and rock mechanics to investigate subsurface conditions. This allows them to evaluate and design activities such as the stability of natural slopes and man-made soil deposits, earthworks with cuts and fills, shallow and deep foundations, dams, retaining walls, tunnels, and many other works directly interacting with the subsoil and water.
In order to meet the diversity of challenges the profession faces, the International Society has created 30 technical committees over the last 50 years, each representing a particular aspect of geotechnical engineering.
Foundation engineering is one important area of geotechnical engineering. The foundation of any structure should be designed to withstand man-made and natural loads, vertical and lateral pressures created by earthquakes and high winds, as well as the weight of the structure itself. Buildings, skyscrapers, bridges, and other superstructures have to bear on shallow footings, mats, or pile foundations. Shoring systems include bracing of deep excavations, nailing of landslides, and the support of tunnels, to name a few. Any geotechnical engineering project is different. Indeed, the soil at a site is likely different from any other site. As a result, the most common first step of any geotechnical project is the site investigation. It starts by drilling into the soil and rock layers, testing them in the field or collecting samples, which can then be analyzed in a laboratory. Once soil and rock properties are determined, the geotechnical engineer can design the project, including its environmental impact. Investigations can include the assessment of the risk to humans, property, and the environment from natural hazards such as earthquakes, landslides, sinkholes, soil liquefaction, debris flows, and rockfalls. Geotechnical engineering can significantly influence the sustainability of infrastructure development because of its early position in the construction process. Given the intensive research carried out in the field, impressive geotechnical advancements are made on a regular basis. Most of these innovations are often hidden from the public eye because the work is underground. These innovations are, however, a crucial part of a success story. They can be temporary in nature, such as deep excavation support to construct a high-rise tower like the Burj Khalifa, or permanently embedded such as the complex foundation system of the Rion-Antarian Bridge. The built environment where we live serves as a dynamic interface through which humans and the ecosystem interact and influence each other. Understanding this interdependence is key to fathoming the impact of geotechnical engineering on society.
Throughout history, geotechnical engineering has made changes in the way we live or even think. Projects like building the Aswan Dam, laying the foundation of the Golden Gate Bridge, digging the Panama Canal, stabilizing the cliffs at Pointe du Hoc, or giving new life to the Tower of Pisa have affected past and present generations. Such projects, large and small, will continue to impact and shape our future. It has been a cycle of sharing knowledge and gaining knowledge, of accomplishments and lessons learned. The International Society for Soil Mechanics and Geotechnical Engineering is proud to be at the center of this field emblematic of human achievement.